Hello everyone, welcome back to another video. I hope you all are doing well. Today we will be solving the another problem of the blind 75 series. Currently we are solving problems on the bit manipulation. So today we will be solving the problem on the same concept. Today we will be solving the 13th problem of the blind 75 series. The problem is counting bits. Let's go to the problem. This is the problem, guys. The problem statement is you are given an integer n. Return an array answer of length n plus 1 such that for each I such that I lies between 0 to n, answer of I is the number of ones in the binary representation of I. Guys, the question says that you will be given an integer n as an input and you need to check the binary representation of each number starting from 0 till n, and in the binary representation of each number, you need to count the number of set bits and you have to put all those counts together in a vector and return it as an answer. So let's understand the question more clearly with the help of an example. Okay, let's assume that you are given the value of n as 5. So what you need to do is you need to check the binary representation of all the numbers that lies in the range 0 to 5, and in the binary representation of each number you need to count the number of set bits. So the ones that are present in the binary representation of any number are known as set bits. So here you can see in the binary representation of 0, we don't have any set bit. So the number of set bits for this would be 0. For 1, it would be 1. For 2, it would be 1. For 3, it would be 2. For 4, it would be 1. And for 5, it would be 2. So what you need to do, you need to put all these counts in a vector and you need to return them as an answer. Okay, now let's proceed towards the solution of this particular problem. Guys, as this problem is based on the bit manipulation, so we will be requiring some bitwise operators to solve this problem. So let's understand the working of some bitwise operators that we will be using in our solution. The very first operator that we would be using is right shift operator. Okay, so let's understand the working of this right shift operator with the help of an example. So as you can see here, it takes two operands. Okay, so as this is a bitwise operator, so it will work on a bit level. So for understanding the working of this operator, we will be requiring the binary representation of these numbers. Okay, so the binary representation of 15 is 1111. Okay, so actually there would be 32 bits. So assume that all the bits that would be before these four ones would be 0. So remaining 28 bits before these ones would be 0. Okay, so if I will perform the right shift operation on this particular number, so what will happen? Each bit each bit will be shifted to right by one position. Okay, and the rightmost bit, which is also known as the least significant bit, will be lost. Okay, so if I will perform the right shift operation on this particular number, so I will lose the last bit or the rightmost bit or the least significant bit. So what I will be left with is 111, and this 111 is equivalent to 7 in the decimal form. Okay, again, if I will perform the right shift operation, so all the bits starting from the very first position would be shifted to right, and I will lose the rightmost bit. So I will be left with two ones. So this is equivalent to 3 in the decimal form. Okay. Again, if I perform the right shift operation, so I will again lose this one. So I will be left with single one. Okay. So this is equivalent to 1 in the binary format. And again, if I perform the right shift on this particular number, so what will happen? I will lose this bit and I will be left with 0 only, which is equivalent to 0 in the decimal format. Okay, guys, let's notice a pattern over here. So initially the number was 15, and when I applied the right shift operation on this particular number, the number became 7. Okay, again when I performed the right shift operation, the number became 3. Next time the number became 1, and finally the number became 0. So guys, can you notice the pattern over here? I hope you have noticed the pattern. So each time when we are shifting the bits to right by one position, the number is actually getting divided by 2. You can see over here, initially the number was 15. When I performed the operation, the number became 7, then the number became 3, then the number became 1, then the number became 0. Okay, so this is, you can say, the property of the right shift operator. So just keep this property in your head because we will be using this property in the next approach. So you should remember that the right shift operator or right shifting the bits by one position is equivalent to dividing the number by 2. Okay, so the another bitwise operator that we will be using here would be bitwise AND operator. So the working of AND operator is quite simple. So you just need to remember one property. The AND operator gives output as 1 only if both the bits are set. Okay, if both the bits or if both the operands are 1, then only the output is 1, and rest in all the other cases the output is 0. Okay, so now let's understand the approach that we would be using to solve this problem with the help of an example. Okay, now suppose we want to calculate the number of set bits in the binary representation of this number 5. Okay, so what I will do, I will start from the rightmost position. So I will check each bit one by one. Let's see how. Okay, so the binary representation of 5 is 101, 101. Okay, so let's ignore all the bits that uh, let's ignore all the bits before this last one. Okay, we only have to focus on this rightmost bit or the least significant bit. So we need to check whether this bit is set or not. So for doing that, we will be using the AND operator. Okay, so uh, I will do the AND of this particular bit with 1. Okay, and the binary representation of 1, you can say it is 0001. Okay, remaining all the position would be zeros. Okay, so as I told you, the answer does not depends upon these bits because as we have 0 here, so it doesn't matter what value we have in the binary representation here. So the value for this particular part is always going to be 0. So our answer will always depend upon the rightmost bit or the least significant bit. Okay, so this will give us answer as 1 only if this particular bit is set or the least significant bit is set. Otherwise the output will always be 0. Here you can see we have 1 and 1 here, so 1 and 1 will give me the answer as 1, and we can see that here is a set bit. Okay, so next time I want to check this bit. Okay, I want to check this bit. So how will I bring this bit to the rightmost position? I told you we will be using the right shift operator. Okay, so what I will do, I will just shift this number to right by one position. So this number will become 10, and again I will perform the AND operation of this particular number with 1. Okay, so let's ignore all the bits before this least significant bit. So 0 and 1 will give me the output as 0. Okay, so we didn't got the set bit here. So what I will do, I will again right shift the number and check for the next number. Okay, so if I will right shift this number, so what I will get 1, and if I will perform the AND operation of this particular one with 1, so I will get 1. Okay, so you can see that I got 2 set bits over here. So in this way, by using the right shift operator and bitwise AND operator, we would be able to count the number of set bits in the binary representation of any number. Now let's quickly write down the code for this particular approach. Then we will analyze the time and space complexity of this approach. So let's declare a vector over here because we need to store the answer in a vector. So let's call this as set bits, and I will start a loop starting from 0 till n. So what I need to do is I need to count the number of set bits for each I. Okay, so let me store this I in some another variable, and let's declare count as 0. Okay, so what I will do, while number is greater than 0, I just need to check if rightmost bit is set or not. So for doing that, I will perform the AND operation of rightmost bit with 1. Okay, so if this is true, I will just increase the count, and for the next iteration, I will consider the another bit. So I will just right shift the number by one place. Okay, so when I will be out of this loop, I will be having the count of the set bits for this particular number. So what I will do, I will just do set bits of I equals to count, and finally I will just return this vector set bits. Okay, let's run this code. Okay, it is working fine. Let's submit this, and yes, it got accepted. Okay, now let's analyze the time and space complexity of this particular approach. Okay, so we are using two loops over here. This for loop will run n plus 1 times. So how many times this while loop will run? Okay, so actually the number of times for which this while loop will run will depend upon this number, and this number is nothing but I am just taking the value of I in it. Okay, so what can be the maximum value of I? The maximum value of I can be n. Okay, so in every iteration what I am doing, I am just right shifting the number by one place. Okay, and you know that the right shifting by number is equal to dividing the number by 2. So each time you can say that I am dividing the number by 2. So when I just keep on dividing the number by 2, the time complexity is of logarithmic order. So you can say that the time complexity for this particular loop will be log n. So time complexity for this particular approach will be n log n. Okay, and the extra space that we are using here is this vector, which is used for storing the count of set bits. So this is the only extra space that we are using in this approach. So the space complexity will be big O of n. Okay, so you can see over here time complexity will be n log n because of this outer loop, and log n for this inner loop, and space complexity is big O of n for this vector of integer that I am using for storing the set bits. So guys, this was the basic approach to solve this problem. Now the question comes, can we optimize this approach? Yes, we can definitely optimize this approach. Let's see how. So for optimizing this approach, we will be requiring some observations. So let's understand these observations first. So the very first observation that I have written over here, I have already explained you this observation in the previous approach, that right shifting by any number x to one place is equivalent to dividing the number by 2. Okay, so right shifting the bits of a number by one place is equivalent to dividing the number by 2. This I have already explained you in the previous approach. Let's come to the second observation. So if you are given any integer value x, so that number x will either be even or it will be odd. Okay, so if the number is even, the least significant bit or the rightmost bit of that particular number will always be 0. So you can see here I have written the decimal and binary representation of some numbers. So if you just pick any even number from here, let's pick 4 and 6 and 10. You can see here in all the even numbers, the rightmost bit or the least significant bit is always 0. Okay, so this is the property you should remember. And if you just take any odd number, so in any odd number, the least significant bit or the rightmost bit is always 1. You can take some examples from here. Let's take 139. So the rightmost bit is 1 in all the in all the odd numbers you can see here in the table. Okay, now let's go to the another observation. So this second observation is very important, and this is the main intuition behind the working of this algorithm. Okay, let's understand this observation clearly. So let's assume that I have already calculated the number of set bits for this particular value 4. Okay, let's assume I know the number of set bits, or I know the count of set bits for this particular value 4. So if I know the count for 4, can I use this count to calculate the number of set bits for any number that comes further? The answer of this is yes. Okay, so I know I can get this 4 from this 8 by right shifting the bits of 8 by one position to the right. Okay, if I will just right shift all the bits of 8 to the one position, by one position I will get this number 4. Okay, so I can also say that I this, like, if I will add just one bit to the add to the rightmost position of this 4, so I can get the binary representation of 8. Okay, so we can say that the number of set bits in this 4 and this 8 will be like almost equal. There will be just one extra bit in the 8. This bit will be either 0 or 1. So if I know what this bit will be, then I will be easy, then by using the, then I can use the count of this particular 4 to count the number of set bits in this particular 8. Okay, so how can I know what is this particular bit? I know this is the rightmost bit or the least significant bit. So how can we know what would be this bit? So this is very simple, guys. I told you here in the first observation that if the number is even, the rightmost bit or the least significant bit is always 1. And if the number is odd, the rightmost bit is always 1. So when we are going from when we are going from x to x by 2, when we are going from 8 to 4, we are actually losing a bit. And if the number is even, the bit that we would be using would be 0. So I am only concerned about the set bit. So this bit will not be, you know, I will not count this bit because I have lost 0. So the number of set bits in x is equal to number of set bits in x by 2 if the number is even. So similarly, when we are going from x to x by 2, here you can see when we are going from 9 to 4, the representation is almost same, but we have just one more bit here. Okay, so when we are going from x to x by 2, I am just losing this rightmost bit. And how can I know what this bit would be? If the number is odd, this bit would be 1 for sure. So we know that if the number is even, if the number is odd, then the number of set bits in x is equal to number of set bits in x by 2 plus 1, because this one would, I would have lost this one bit when I'm going from x by 2, when I'm going from x to x by 2. Okay, so just keep this point in mind that number of set bits in x is equals to number of set bits in x by 2 if the number is even, and number of set bits in x is equals to number of set bits in x by 2 plus 1 if the number is odd. So we will be using this property to solve this problem in the optimized way. Okay, so let's, use the above property to fill this table. Okay, I need to count the number of set bits if n is equals to 5. Okay, so how I can count it using this approach, let's see. Okay, so I know this one is a odd number, and if the number is odd, then the number of set bits is equal to number of set bits in 1 by 2 plus 1, and 1 by 2 is nothing but 0, because we will be taking the integer value, plus 1 is 1. So number of set bits for 1 would be 1, and for 2, so 2 by 2 is 1. So if number is even, number of set bits in x is equal to number of set bits in x by 2, so it would be 1. 3 is odd, so number of set bits in 3 would be number of set bits in 3 by 2, that is 1 plus 1, so 1 plus 1 would be 2. For 4, it would be 4 is even, so number of set bits in 4 is equals to number of set bits in 4 by 2, that is number of set bits in 2, so it would be 1. Okay, and for 5, then 5 is a odd number, so number of set bits would be number of set bits in x by 2, that is 5 by 2, which is actually 2 plus 1, so it would be 2. Okay, so the answer is 0 1 1 2 1 2. Let's verify this answer whether this is correct or not. So you can see here the answer is 0 1 1 2 1 2. Okay, so in this way, by using this approach, we will be easily able to solve this particular problem. Now let's quickly write down the code for this particular approach. Then we will analyze the time and space complexity of this particular approach. So we need a vector to store the count of set bits. So we will use a loop. Okay, so before that, what I will do, I know that the number of set bits for 0 would be 0. So I will start a loop from 0 1, and I will go till n. Okay, I just need to check if the number is even or odd. So let's check for odd first. So if the number is odd, if the rightmost bit is 1, so what I will do, I will just do I and 1. If this gives me true, it means the number is odd. So set bits of I will be set bits of I by 2 plus 1. So else the number is even. So if the number is even, then the set bits of I is equals to set bits of I by 2. Okay, so at last I will just return this vector. Let's run this. Okay, it is working fine. Let's submit this code, and guys, it gets accepted. So what will be the time complexity? So you can see here we are just iterating, we are just going from I equal to 1 to I equal to n. So time complexity will be uh, big O of n, and the space complexity will be again big O of n, because we are just using this vector of integer to store the count of set bits. So in this way we can solve this problem in the optimized manner. So this is all for today's video. We will meet in the next video. Bye bye. Take care.